Classical deterministic physics operates as a closed loop. In a strictly mechanical system, every action is the direct, inevitable result of a predetermined physical cause. If the universe operates exactly like clockwork, it creates a severe philosophical consequence for human biology. The mind is reduced to a mere epiphenomenon. An epiphenomenon is a secondary effect occurring alongside a primary process, possessing no causal influence over it. In a closed loop, consciousness is merely a passive spectator watching the brain execute commands. However, quantum mechanics disrupts that clockwork. A system exists as a probabilistic wave function until observed, instantly collapsing into a single discrete measurement. This breaks classical determinism, creating a mathematical gap between probability and actuality, an opening where subjective consciousness might influence physical reality. The concept of quantum consciousness is frequently dismissed by critics as a monolithic category of mysticism. In reality, it is a highly differentiated spectrum of physical and philosophical models. This is Robert Lawrence Kuhn's 2024 Landscape of Consciousness. It maps a comprehensive taxonomy of theories explaining subjective experience. Zooming in on the left, the yellow node isolates the quantum approach. It outlines 16 subtheories of consciousness based on quantum mechanics. For the theorists in this section, quantum mechanics provides the only mathematically viable causal gap for the subjective mind to exert agency over objective matter. The most debated theory on the map is orchestrated objective reduction, or Orch-or. It was developed by mathematician and Nobel laureate Roger Penrose. Penrose bases his model on the premise that human consciousness requires a non-computational process. A non-computational process is a mathematical operation that cannot be simulated or executed by any standard algorithmic computer. To ground this requirement in physics, he proposed objective reduction. In this mechanism, quantum states collapse into definite physical outcomes due to instabilities in the fine-scale geometry of space-time and gravity. Mainstream neuroscience typically rejects the application of quantum mechanics to the brain. Biologists argue it is too warm and wet, causing instant environmental decoherence. Environmental decoherence is the process where a fragile quantum state interacts with its chaotic surroundings, forcing it to lose its quantum properties and behave like classical matter. Anesthesiologist Stuart Hameroff proposed a biological hardware solution, microtubules. These cylindrical protein polymers form the structural scaffolding inside brain neurons. They contain an insulated core that protects quantum states from surrounding thermal noise, sustaining quantum coherence long enough to achieve objective reduction. Orch-or attempts to anchor the mind directly into the physical structure of the brain by utilizing undiscovered physics that link quantum events to gravity. Several theories abandon biological hardware and focus entirely on the act of measurement. These models build on the mathematical legacy of physicist John von Neumann. Mathematical physicist Henry Stapp constructs his framework around the concept of the asked question. Stapp notes that the Schrödinger equation maps how quantum probabilities evolve, but nothing in the mathematics determines which specific experiment is actually set up. An apparatus like a Geiger counter forces a discrete yes or no question onto a quantum system, but physics itself cannot dictate the choice. Stapp concludes that an independent consciousness must be the entity selecting the actual event. Under this logic, the mind is a required actor in the physical universe, not a spectator. Physicist David Bohm approached the ontology from a different direction, proposing the implicate and explicate order. Bohm argued for undivided wholeness. The observer and the observed are not separate substances, but related projections unfolding from a deeper, higher-dimensional reality. Philosopher Pavel Pilttunen extends Bohm's model by introducing active information. This proposed form of quantum potential energy provides a non-mechanical mechanism for the mind to influence physical systems. Within these frameworks, conscious observation acts as the physical mechanism that solidifies reality. Another branch of the taxonomy attempts to formalize the rules of subjective experience through theoretical computation and information theory, starting with computer scientist Stephen Wolfram. Wolfram embeds consciousness in a concept he calls the Roolead. The Roolead is the entangled, absolute limit of all possible computational rules executing in all possible ways.
Wolfram defines consciousness as how branching brains perceive a branching universe. It extracts a single, coherent thread of experience from infinite computational possibilities. Rather than advanced computational power, it is a step down that formulates sequential physical laws from chaos. Zooming back into the microscopic biology of the brain, physicist Friedrich Beck and neurobiologist John Eccles modeled a theory of quantum neurobiology. They focused on synaptic exocytosis, the chemical mechanism neurons use to transmit signals. Because the physical channels are incredibly small, the exact location of a triggering ion exists as a spread-out quantum wave packet rather than a fixed point. Eccles theorized that mental intention dynamically alters the probabilities of these quantum wave packets collapsing. By selecting which ions trigger neurotransmitter release, the mind physically drives neural firing. Theoretical biologist Stuart approaches the physics through a non-substance dualism, relying heavily on Werner Heisenberg's ontological interpretation of the quantum state. Kaufman proposes that the mind collapses the wave function to convert res potentia, which are ontologically real possibilities, into res extensa, which are actuals that occupy physical space. Whether parsing abstract computational algorithms or shifting synaptic probabilities, these theories position consciousness as a selective filter that turns raw potential into discrete physical reality. The furthest nodes push these concepts to their limits. Physiologist John Torday grounds consciousness in cellular symbiogenesis, embedding quantum mechanics directly into the cell membrane. Symbiogenesis is an evolutionary theory where new, complex life forms are created through the merging of distinct organisms. Torday argues that quantum entanglement acts as a physical bridge, linking local cellular consciousness directly to the non-local cosmos. Physicist Lee Smolin organizes the problem through his causal theory of views. Smolin calculates that physical reality is built entirely from the partial information available at any specific event. He defines consciousness as the physical correlate of only those rare original relational views that have no prior duplicates in universal history. Mathematician Bernard Carr argues that standard physics is insufficient. He states we need a higher dimensional geometry called mental space to mathematically accommodate the first-person perspective. Physicist Federico Faggin introduces a model called quantum information-based panpsychism, or QIP. Faggin postulates that any system in a pure quantum state inherently possesses qualitative self-knowledge. The quantum system physically feels its own state through subjective experience, known in philosophy as qualia. Condensed matter physicist Matthew Fisher attempts to pull these vast properties back into local biology with a framework called quantum cognition. Fisher identifies the nuclear spins of phosphorus atoms as viable neural qubits. He proposes these qubits are protected over long periods by binding into calcium phosphate clusters called Posner molecules, acting as a functional quantum memory for the brain. The remaining nodes rely on dense, highly specialized mathematics, from Gordon Globus mapping thermophile brain dynamics to Roman Poznansky defining dynamic organicity theory across multiple biological scales. Finally, physicist Carlo Rovelli brackets the entire map with relational physics, using quantum mechanics to argue that the physical world is inherently perspectival. The divergence within these models demonstrates that applying quantum mechanics to the hard problem necessitates a reevaluation of our definitions of space, time, and biology. The landscape divides into two primary metagroups. The first relies on biological quantum processing. Penrose, Eccles, and Fisher argue evolution uses quantum mechanics to generate consciousness. The second relies on fundamental ontology. Stapp, Kaufman, and Faggin argue reality and the mind are ontologically codependent. Mainstream physicalists continue to dismiss these models. The primary criticism is that quantum theories of consciousness simply attempt to explain one intractable mystery by attaching it to another. But that skepticism ignores the mechanical dead end of the alternative. Classical materialism remains a causally closed system, unable to explain exactly how subjective feeling arises from deterministic matter. The mathematically rigorous, probabilistic nature of quantum mechanics provides a distinct opening.
It remains a rigorous, non-mystical frontier for explaining how the subjective mind exerts true agency over the physical universe.